The Aurora Borealis, also known as the Northern Lights or Polar Lights, is a breathtaking natural phenomenon that has captivated humans for centuries. These shimmering curtains of light dancing across the night sky have inspired awe, wonder, and countless myths and legends. But beyond their ethereal beauty, auroras hold valuable scientific secrets about our planet's interaction with the sun and the universe. Join us on a journey to uncover the mysteries of the Aurora Borealis, exploring how these celestial displays occur, their impact on Earth, and the fascinating research that continues to unlock their secrets. When most people hear about auroras, they probably think of the Northern Lights, those iconic green, red, and purple hues that dance across the night sky in the Northern Hemisphere. However, auroras also occur in the Southern Hemisphere, and are known as the Aurora Australis. Both auroras are essentially the same phenomenon, differing only in their location relative to the Earth's poles. Auroras happen when charged particles from the sun, primarily electrons, are accelerated by magnetic fields and collide with atoms and molecules in the Earth's upper atmosphere. When the electrons collide, they transfer their energy to the atmospheric particles, causing them to become excited and emit light. This process, known as chemiluminescence, is the same principle behind many neon signs and glow sticks. Auroras typically occur in high-latitude regions such as Norway, Finland, and Iceland in the north, and New Zealand and Tasmania in the south. And while the exact mechanism has been known since the late 19th century, there's still much we don't understand about this complex phenomenon. One area of active research is the study of auroral kilometric radiation, or AKR, which refers to the radio waves emitted during auroral activity. Understanding AKR can help researchers learn more about the fundamental physics of auroras and the interactions between the Earth's magnetic field and the solar wind. Another fascinating aspect of auroras is their ability to be triggered by both solar activity and geomagnetic storms. Solar activity refers to the dynamic processes that occur on the sun, such as sunspots and solar flares, which release bursts of energy and charged particles into space. Geomagnetic storms, on the other hand, occur when these solar particles interact with the Earth's magnetic field, causing it to fluctuate and release energy. Both types of events can trigger auroras, but their relative contributions vary depending on factors like the strength of the solar wind and the Earth's magnetic field. One way scientists study auroras is through in situ measurements taken by satellites that fly directly through them. By analyzing the composition and behavior of the charged particles within auroras, researchers can gain insights into the physical processes that drive these phenomena. For example, the European Space Agency's swarm constellation of satellites has been studying the Earth's magnetic field since 2013. One of its primary goals is to measure changes in the magnetic field caused by auroral activity, providing valuable data for understanding the dynamics of these phenomena. Ground-based observatories play an equally important role in advancing our understanding of auroras. The University of Alaska's Geophysical Institute, for example, maintains a network of stations across the state that monitor auroral activity. These stations provide continuous data on the timing and intensity of auroras, as well as information about the local conditions that may influence their occurrence. By collecting this data over long periods of time, researchers can identify trends and patterns in auroral behavior and correlate them with solar and geomagnetic activity. One of the most exciting recent developments in auroral research has been the use of new imaging techniques to capture stunning views of these phenomena. The Aurora Borealis in Norway, captured in this image, is just one example of the breathtaking imagery that's helping to advance our understanding of these celestial displays. Traditional auroral research relied heavily on ground-based observatories and in situ measurements. However, these methods have limitations. Ground-based observatories can only measure auroras at specific locations and may not capture the full extent or dynamics of these phenomena. In situ measurements, on the other hand, provide valuable data, but they're limited to the specific location and time frame of each satellite's mission. Fortunately, advances in imaging techniques have overcome some of these limitations. Imaging auroras from space provides a unique perspective on these phenomena, allowing researchers to observe their size, shape, and evolution over time. The European Space Agency's swarm satellites, for example, have captured stunning images of auroras that have helped researchers better understand the dynamics of these phenomena. These observations have revealed new insights into the structure and behavior of auroras, providing valuable information about the physical processes that drive them. Aurorae are classified based on their location, shape, and color. One common classification system divides auroras into four main types: diffuse, rayed, searchlight, and arc. Diffuse auroras are widespread and relatively faint, covering large areas of the sky with a soft glow. Rayed auroras, on the other hand, appear as a series of distinct rays or bands that extend outward from the center of the magnetic field lines. Searchlight auroras are more localized and intense, resembling a beam of light focused on a specific area. Arc auroras form as a result of the merging of multiple auroral forms and appear as continuous arcs or bands of light. The colors of auroras are determined by the type of atmospheric particles that are being excited by the colliding electrons. Most commonly, auroras appear in shades of green, red, and purple. Green auroras, which are the most frequently observed, occur when electrons collide with oxygen atoms at low altitudes. Red auroras, on the other hand, occur when electrons collide with oxygen molecules at higher altitudes. Purple auroras, also known as red-free auroras, are less common and occur when electrons collide with nitrogen molecules. Beyond their natural beauty, auroras have significant implications for various technologies and infrastructure. For example, auroras can disrupt important communication systems such as the Global Positioning System, or GPS, by interfering with the signals that satellites use to communicate with receivers on the ground. This can cause errors in positioning and timing, which can be problematic for industries that rely on precise measurements, such as transportation and telecommunications. Additionally, auroras can induce electric currents in structures like power lines and pipelines, which can damage equipment or even pose safety risks. Understanding the patterns and intensity of auroral activity is therefore crucial for mitigating these potential disruptions and protecting critical infrastructure. In recent years, scientists have made significant progress in understanding the complex phenomenon of auroras. One notable achievement was the 2022 Nobel Prize in Physics, which was awarded to Alan Aspect, John Clauser, and Anton Zeilinger for their experiments with quantum entanglement, a phenomenon that plays a crucial role in the behavior of charged particles within auroras. By studying quantum entanglement, these researchers have helped to deepen our understanding of the fundamental nature of reality and the laws that govern it, including the behavior of particles in auroras. Another exciting development has been the use of machine learning and artificial intelligence to analyze auroral data and make new discoveries. Machine learning algorithms can identify patterns and correlations in large datasets that would be difficult or impossible for humans to detect, providing new insights into the behavior of auroras. For example, researchers have used machine learning to analyze data from the swarm satellites to study the evolution of auroras over time and to identify key factors that influence their formation. As technology continues to advance, we can expect even more exciting discoveries about auroras and their role in our planet's interaction with the universe. One promising area of research is the use of citizen science to collect data on auroras around the world. By engaging the public in scientific research, citizen scientists can help researchers gather data in more locations, leading to a more comprehensive understanding of auroral activity. Additionally, the development of new instruments and observation techniques is constantly improving our ability to study auroras. For example, the James Webb Space Telescope is expected to provide unprecedented views of auroras on other planets, which will help researchers better understand the behavior of these phenomena in different environments. Auroras are not only a spectacular natural phenomenon, but also a window into the fundamental laws of our universe. By unraveling the mysteries of auroras, we gain a deeper understanding of our planet's place in the cosmos and the forces that shape our world. As we continue to explore and study auroras, we can expect even more breathtaking discoveries that will inspire future generations of scientists and stargazers alike. If you enjoyed this video, don't forget to like and subscribe for more updates on all our videos. If you want to support us, please consider becoming a patron, where you'll get access to exclusive content and the chance to vote on our next video topics. Thanks for watching, and we'll see you next time.